Lowe's has the Labor Day deals you need to give your home a new look. Buy one, get one free select interior paint via Visa gift card rebate. Then, add the final touch with 2 for $8 on select 2.5 or 3-quart mums. Refresh your home and save big while doing it. Lowe's, we help, you save. Valid through 9/3. Mums offer in-store only. Selection varies by location. While supplies last. More terms and restrictions apply. See Lowes.com/rebates for details.
Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. This week in astronomy, Bennu, a time capsule, hunting cosmic rays with neutrinos and before the Big Bang. Bennu, a time capsule from the early solar system. Asteroid Bennu is an object made of many different kinds of material, some of which come from very far parts of the solar system and even from outside it. Over billions of years, these materials were changed by water and by the tough conditions of space. We now know this because NASA's OSIRIS-REx mission brought pieces of Bennu back to Earth in 2023. Scientists from all over the world are studying them, with leadership from the University of Arizona. Bennu itself is not one solid rock but a collection of fragments that once belonged to a larger asteroid. That asteroid was shattered by a collision, probably in the asteroid belt between Mars and Jupiter. The parent asteroid contained materials from close to the Sun, from far away in the solar system, and even from other stars. This means Bennu preserves a record of the early days of our solar system, more than 4 billion years ago. By analyzing the samples, scientists discovered grains of stardust, tiny particles that were formed in other stars long before our solar system was born. These grains can be recognized because their atomic fingerprints are different from anything made inside our solar system. Researchers also found unusual organic material that likely came from interstellar space, along with solid matter formed near the Sun. This shows that Bennu holds a mixture of ingredients from many different regions. The studies also revealed that Bennu's parent body contained a lot of ice. Over time, this ice melted, creating liquid water that reacted with minerals at temperatures similar to room temperature. These chemical reactions changed much of the material inside the asteroid, forming new minerals that still hold water within them today. In fact, around 80% of the minerals in Bennu's samples carry evidence of water. This means that the asteroid's interior once went through long-lasting water-driven processes, similar to very slow chemical cooking. But water was not the only factor. Bennu has also been hit by tiny meteorites and exposed directly to the solar wind because it has no atmosphere. These conditions left microscopic craters and melted spots on its surface, proving that Bennu has been constantly reshaped by what scientists call space weathering. This process seems to happen more quickly than researchers expected. All of these results show that Bennu is like a time capsule. It contains pieces of ancient stars, organic molecules, minerals that reacted with water billions of years ago, and signs of constant bombardment in space. This makes it one of the best records we have of what the early solar system was made of and how it evolved. Unlike meteorites that fall to Earth, Bennu's samples were collected directly in space, without being contaminated by our atmosphere, which is why missions like OSIRIS-REx are so important for understanding our cosmic history. Hunting cosmic rays with neutrinos. Scientists are trying to figure out where cosmic radiation comes from, and they are using a special kind of particle called neutrinos to help them in this search. Neutrinos are useful because they can travel across the universe without being stopped or changed much by matter, which means they carry information straight from their source to Earth. To detect them, researchers use a huge observatory called IceCube, buried deep in the ice at the South Pole. Since 2009, an international team has been running IceCube, and recently a group led by Professor Anna Franskaliak in Bochum developed new computer methods that make it much easier to analyze the data. These methods can calculate the energy and direction of a neutrino in about 30 seconds, and the result is shared immediately with telescopes all over the world. That way, astronomers can quickly point their instruments at the right spot in the sky to look for possible sources, such as galaxies, black holes, or other powerful cosmic events. The system is also refined later with slower but more accurate calculations, which are now 4 to 5 times better than before. This speed matters because some of these cosmic events are very short-lived and can be missed if telescopes are not directed in time. The researchers also used their algorithms to go back and recheck older data collected by IceCube. In doing so, they had to rule out some previously suspected sources. For example, they had thought that tidal disruption events might produce neutrinos. These events happen when a star passes too close to a quiet black hole, and the black hole's gravity stretches and rips the star apart. In earlier data, 3 neutrino detections seemed linked to such events. But when the team reanalyzed the trajectories with the improved method, they found the neutrinos did not actually come from the same places as the tidal disruption events. So far, no definite source of cosmic radiation has been identified, but the improved tools give researchers a much better chance of solving this mystery in the future. Their work has already produced 3 scientific publications, including one in a major astronomy journal and 2 shared online for the scientific community. Before the Big Bang, Simulating the Unknown. Scientists have long debated what, if anything, happened before the Big Bang. Some say the question makes no sense, because the laws of physics break down when we try to trace the universe back that far. But a new study by researchers in London and Oxford suggests a way forward, using advanced computer simulations to explore extreme cosmic conditions where pen and paper calculations fail. Einstein's theory of general relativity describes how gravity works and how matter and energy move through spacetime. Normally, cosmologists simplify these equations by assuming the universe looks the same in all directions and is evenly spread out. This is a good description of the universe we see today, but when you rewind the clock to the Big Bang, those assumptions may no longer hold. Pushing the equations to that limit usually leads to a singularity, a point of infinite density where the theory stops working. That's the same problem physicists face when trying to describe what happens inside black holes. The new idea is to rely on a branch of physics called numerical relativity. Instead of solving Einstein's equations exactly, which is impossible in extreme situations, scientists program computers to approximate the solutions step by step. This method was originally developed decades ago to predict what would happen if 2 black holes crashed together. It became especially important after the LIGO experiment was proposed to detect gravitational waves, and in 2005 researchers finally managed to model such collisions successfully. That breakthrough showed that numerical relativity can solve problems too complex for traditional methods. Now, scientists hope to use it to investigate early universe mysteries. One of these is cosmic inflation, the rapid expansion that supposedly happened just after the Big Bang. Inflation explains why the universe today looks smooth and uniform across vast distances. But physicists still don't know what caused inflation or how it started. The trouble is that when they try to study it with Einstein's equations, they must already assume the universe was uniform in the beginning, which inflation was meant to explain in the first place. Numerical relativity could let them test more complicated, less tidy starting points, perhaps even predictions from string theory. Beyond inflation, the technique could also help explore other fascinating possibilities. It might show what kind of gravitational waves would be produced by cosmic strings, hypothetical defects in spacetime left over from the early universe. It could also help look for traces of our universe bumping into another one, which would support the idea of a multiverse. And perhaps most strikingly, it could test scenarios in which the universe did not begin with a single Big Bang, but instead goes through endless cycles of collapse and rebirth, so that something existed before our cosmos began. Running these simulations is extremely demanding, requiring supercomputers and sophisticated programming. but as computing power grows, researchers expect major progress. The team behind the new paper hopes their work will bring together two communities: cosmologists, who have big questions but often lack the tools to solve them, and numerical relativists, who have powerful techniques but usually focus on black holes rather than the universe as a whole. By combining forces, they believe science might finally move closer to understanding what really happened before the Big Bang.